Welcome to everyone. My name is Víctor López, and I'm presenting my work entitled Combined Heat and Power using High-Temperature Proton Exchange Membrane Fuel Cells for Housing Facilities. This work has been done together with Guillermo López, Ramon Costa-Castelló, and Carlos Batlle. We all come from Instituto de Robótica e Informática Industrial, from CSIC and UPC, Universitat Politécnica de Catalunya, in Barcelona, Catalonia, Spain. And Carlos Batlle comes from Instituto de Organizació i Control, also from UPC. First of all, today's contents. I will start the presentation with a brief introduction. I will move on to the system model, both simulation model and control model, then to control objectives, and the control algorithm used, which is model predictive control and its formulation. Finally, I will present the results obtained from simulation and conclusions. Introduction. Hydrogen has proven to be a good solution for future applications in terms of housing and heat and power, combined heat and power specifically, as is able to increase the efficiency up to 80% when heat is properly used together with electrical power, and waste heat obtained from the chemical process that undergoes inside a PEM fuel cell. PEM fuel cells, which their high temperature version is useful for this kind of housing applications. That's why we've used this kind of systems for our work. So the system basically has first a PEM fuel cell, which is works with a fuel which is hydrogen, which is directly proportional to fuel cell current. Then this fuel cell produces both electrical power and heat, which we also call thermal power. This electrical part of the system on the top of the diagram has a DC-DC converter to regulate voltage, and an electrical battery, which will store energy to be used when the electrical demand needs this energy. Similarly, we have a heat exchanger able to convey and capture this extra heat from the fuel cell, store it in a water accumulator by heating water, that will be used for when the demand of space heating or human needs of hot water are required. This fuel cell has we present here the fuel cell's characteristic curves, polarization curve, which is voltage versus current density, and the power curve, which we can see in blue the electrical power, and in red the thermal or power or heat. This system has been built in MATLAB Simulink using, first of all, we have the same parts we've shown before, which is PEM fuel cell together with its current input, which is hydrogen. Then we have the battery, the accumulator, and we have thermal load and electrical load. Thermal load are those coming from thermal demand, as well as all, other internal variables I will show later. And the same happens with the electrical load. Electrical load basically is thermal demand, and also other internal variables that go from the electrical part of the system to the thermal part, or the other way around in case it's needed. So there are some variables which can be controlled to improve the system. First of all, so this is that's the reason why we use control. We build a control model. This control model has three types of variables. First of all, state variables. State variables are battery and water accumulator energy. Then we have input variables we can modify to change the system's behavior. These variables are fuel cell current, directly proportional to the hydrogen consumption. Then we have transfer power transfer from the electrical part of the system to the thermal part in case extra heat is needed. This is done using a resistance that produces heat. Then also in case it's needed, we can supply or we can get electrical power from the grid. These are variables 3 and 4. And finally, extra heat is released to the environment in case the accumulator is reaching its water boiling point, and that's why we have this fifth input value. Finally, disturbances are electrical and thermal demand. This model is can be summarized using a state space representation with the previously presented variables and matrices A, B, G, D, and C, which all of them include water's characteristics variables, parameters, also the environment parameters, as well as the heat exchanger efficiencies, converter efficiency, and nominal values. This model is the one used for control purposes and is a discrete model. So it's used to calculate the future value based on current values for each iteration. Once this model has been presented, then control objectives are detailed. Those are basically based on minimizing 5 groups of targets. First of all, hydrogen consumption. We want consumption to be low, and we want it to be stable, not really time changing for degradation methods, degradation issues that may appear in the fuel cell if it changes too fast. Also, switching between sources should be it's important that it's available, but shouldn't be done every iteration. So for operational reasons, it's better to have maximum time possible as the fuel cell supplying, and maybe sometime the grid, or maybe sometime the battery, but not switching all time from one to the other. Then electrical power is transferred from the electrical part to the thermal part in case it's needed, as well as the grid connection, which is used in case it's needed. And finally, heat is released to the environment, but it shouldn't be used all the time for space heating problems in the place where the device operates, and this variation shouldn't be really high. So all this is summarized in a model predictive control algorithm based on basically consists on an optimization problem with both objective function and constraints, which is solved for each iteration, and also in each iteration we solve this iteration and some iterations in the future, so that the system can see the tendency and prepare for future changes. Objective function, as seen before, we have several objectives, basically 11. These 11 objectives are weighted in terms of importance using weight functions, and the optimization is used for constrained by some group of equations, which are basically divided into 4. First, the model itself, then the operational values in terms of physical limitations of each of the variables, so maximum temperature, of water in the tank, minimum state of charge of the battery, etc., etc. Then we include binary variables to ensure that switching between one source to the other is possible, although it shouldn't be done every time switching from one to the other. We would like to have at least long periods of one source working and the other one's not working. And finally, sub-constraints for electrical battery and water accumulator are used so that not to reach the top and the minimum level, but at least have some margin for security reasons and to prevent degradation of the battery, for example. This formulation leads to simulations. What we've done is simulate a whole day and divide it into periods of 15 minutes. We have then conclusion, we have 97 iterations with weight functions selected, prioritizing efficiency, fuel cell as the main provider of power, grid when needed, but only when needed. Heat coming from the accumulator should be the heat that in the system should use, and only use the one coming from the electrical part in case it's needed. Then sub-constraints are maybe the most complex constraints we're using, so I present them here briefly. We can see that state variables are limited, for example, in the case of the battery, with a maximum and minimum hard constraints, but also some limits which are close to the border, but are better in terms of degradation and so on, that we don't reach those levels, or at least we don't stay that so much time above or below those levels. Finally, switching from one system to the other in terms of battery and the accumulator this is done using constraints, using binary variable y sub k, the same thing we did in the previous electrical batteries energy limits, in which we used a binary variable which was a sub k. And this is done so that we can use the energy from the grid if needed, or release heat if needed, and so on and so forth. So once we've done this, these are the first results we present. We present a system which is a house in a cold place, but not so Mediterranean place, but close to the mountains. It has a demand in this case for January, the most demanding month, as we can see, basically battery change and accumulator change stay between limits. Battery change even stays between sub-constraints perfectly, as accumulator the water accumulated in the accumulator receives so it decreases its temperature abruptly. That's because winter and thermal demand is really high, and that's the reason why electrical to thermal power needs to be transferred in this case. This is the bottom right graph. But although this could be solved by using a bigger accumulator tank, this would prove, will be seen later, that it's not the best option because it's expensive, but may only be the solution for 1 month and too expensive for the other month. That's why we do control. Fuel cell current, to end up with, stays within limits and is, as expected, the main source. As we saw in the previous one, in January, we had to provide extra heat from the electrical part, and now we have the opposite way around, which is the system produces so much heat that we need to release it to the environment. That's the bottom right graph. So that's why it makes sense to have this size of accumulator, which in this case, you can see that increases its water temperature even above the soft constraint, but luckily not reaching the water's boiling point, which is fine. battery change stays within limits, and the fuel cell current is varying more than before, but is working as expected. So as a conclusion, the system has been designed and presented for a particular house and powered by a fuel cell. Also, switching has been enabled between systems, and the model predictive control strategy presented is able to ensure that the system works perfectly in different scenarios, winter and spring. All variables stay within limits, and maybe as a future work, we would want to have with better select better weight functions to mitigate the system degradation, and have a more complex system and data to test the algorithm.